looking at the series, the sum as n goes from 1 to infinity of negative 1 to the n plus 1 divided by the square root of n plus 1. We are going to test it for convergence or divergence. This is an alternating series. We know that because of the negative 1 to the n plus 1. Folks, it would be alternating whether it was negative 1 to the n plus 1, n minus 1, or simply n. All that will affect is which, if the first term is positive or negative. The alternating series test comes in two parts. I like to do part 2 first. Part 2 is the one where we check the limit. And the reason for that is if the limit is not 0, we're done. So we're going to look at the limit as n approaches infinity. And remember, in the statement of the theorem, it was the limit of the b sub n's, and those are positive. We don't put the negative 1 to the n plus 1 inside of the limit expression when we're finding the limit. So here we have the limit as n approaches infinity of 1 over the square root of n plus 1, which as n approaches infinity does become 0. Yay, we're good there. Now for the first part. Can we say without a doubt that the nth term, 1 over the square root of n plus 1, is in fact larger than the n plus first term, 1 over the square root of n plus 2? Well, in this case, the answer is yes, because n plus 2 is a larger denominator, and so is a smaller overall result. And so we do have that b sub n is greater than b sub n plus 1, and those are the two parts of the alternating series test. We conclude that the series is convergent by the alternating series test. Ran out of room there. Now, folks, if you have been watching, you see that the alternating series test has two parts. If for any reason you did not do two parts, you did not perform the alternating series test. You have to think, like, why am I telling you that? Because I see people's exams. Just think on that for a little while. Once we've determined that an alternating series is convergent, then we have to do some additional work to determine whether that convergence is conditional or absolute. And for that, what we do is we take basically the absolute value of the original series. And so I have the original series here, and I'm going to replace the numerator with simply 1. And now what I'm doing is I'm testing this entirely new series. The sum as n goes from 1 to infinity of 1 over the square root of n plus 1 using any appropriate test. So I might try the comparison test. 1 over the square root of n plus 1, since it has a larger denominator, is smaller than 1 over the square root of n, but since 1 over the square root of n is divergent, having a series that's smaller than 1 over the square root of n, a divergent series, doesn't help. And so the comparison test won't do us any good here. And what we need is the limit comparison test. So we're going to look at the limit as n approaches infinity of 1 over the square root of n plus 1 divided by 1 over the square root of n. So that's going to be times the square root of n. So that's the limit as n approaches infinity of the square root of n over the square root of n plus 1. And I'll divide numerator and denominator by 1 over the square root of n. That gives me the limit as n approaches infinity of 1 over the square root of 1 plus n, and that limit is equal to 1. Note that that 1 is positive and finite. So just to remind us, that means that the two series that we're comparing, 1 over the square root of n plus 1 and 1 over the square root of n, will do the same thing. Since sigma 1 over the square root of n is a p series with p less than or equal to 1, it is divergent. Thus, sigma 1 over the square root of n plus 1 is divergent by the limit comparison test. So what we have is the alternating series is convergent, but the absolute value of the series is divergent. Therefore, the series is conditionally convergent. And that's the final answer for this one. Next up, we're going to do the same thing, test for convergence or divergence. We are looking at the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times n e to the negative n. First, we note that this thing is alternating. Cool. So we run the alternating series test. I do it in reverse order. We're going to look at the limit as n approaches infinity of the absolute value of the terms, right? We drop the negative 1 to the n plus 1. We have n over e to the n. I'm interpreting the negative n exponent as putting the e to the n in the denominator. Well, this limit is going to be infinity over infinity. I need to use L'Hopital's rule, but I cannot use it on a non-continuous function. Therefore, when we find the limit, we're actually going to find the limit as not n, but x approaches infinity of x over e to the x. And by L'Hopital's rule, this becomes the limit as x approaches infinity of 1 over e to the x, which is equal to 0. It follows that the limit with n is equal to 0, and we have part 2 of the alternating series test done. I really just want to emphasize, folks, anytime you're doing calculus with any of these expressions, whether it's integrating or differentiating, well, they're not taking a limit, so it's not all calculus. Anyway, if you're either integrating or differentiating, please, please, please don't have your expression in terms of n. It should be in terms of x. Now let's move on to the first part of the alternating series test. We want to know if n over e to the n is bigger or smaller than n plus 1 over e to the n plus 1. We've got the denominator getting bigger, so that's promising, but we also have the numerator getting bigger, and so I'm going to call this not obvious. Now, folks, on exams, I get people writing things like, well, this is growing faster than this, the denominator is growing faster. I will never talk about which one is growing faster. I talk about whether the relationship is obvious, and if it's not, I don't force it. We have other tools that we can use. I'll show you 2 of them. One of them is we can differentiate the function, or I should say the related function, f of x is equal to x e to the negative x. You see, that's the same as the terms in terms of n, except it's now in terms of x. If we take a derivative and the derivative is negative, then we know the thing is decreasing. F prime of x, using the product rule, is going to give us e to the negative x times the quantity of 1 minus x. You can go ahead and check it. Turns out that this is negative as long as x is bigger than 1. Therefore, b sub n plus 1 is less than b sub n. We've satisfied that the thing is decreasing. Decreasing with a limit of 0, the series is going to converge. I fit it all in there. The series is convergent by the alternating series test. Now, I said there was another way to show that this thing was decreasing, and here it is. Or, let's make the assumption that n over e to the n is greater than n plus 1 over e to the n plus 1. And then we're going to use a series of if and only if statements. So this is true if and only if, cross multiply. We can do that because our denominators are positive. N e to the n plus 1 is greater than e to the n times the quantity of n plus 1. At this point, we can divide e to the n on both sides, or I should say divide by e to the n on both sides. And the inequality that we have is true if and only if n times e, having trouble getting my colors straight, is greater than n plus 1, which is true if and only if ne minus n is greater than 1. Bear with me here, we're almost there. Which is true if and only if, factoring out the n and then dividing, we get n is greater than 1 over e minus 1. Now 1 over e minus 1 is approximately 0.6. Therefore, as long as n is bigger than 0.6, and we're talking about n going to infinity and starting at 1, so n is bigger than 0.6, then the reverse of all these if and only ifs are true, which means that, yep, we have a decreasing function. So that's an alternative way to show that the series terms are decreasing. In either case, our conclusion is that the series is convergent by the alternating series test. Now, generally, we would go through and determine whether that convergence is conditional or absolute. And so we'd start with the sum as n goes from 1 to infinity of n e to the negative n. But it turns out that the appropriate test we haven't seen yet. I would use the ratio test on this, and that's going to be in a future lesson. Once you've seen that, maybe come back to this, perform the ratio test, and you'll see that it turns out to be absolutely convergent. Let's see if we can squeeze one more in. Don't look at that timestamp. You don't have any idea how long this is going to take. The sum as n goes from 1 to infinity of negative 1 to the n minus 1 of the arctangent of n. It's clearly alternating because of the negative 1 to the n minus 1. Let's start with part 2 of the alternating series test. The limit as n approaches infinity of the arctangent of n. Folks, the limit of the inverse tangent function as n approaches infinity is equal to pi over 2. If you're not sure about that, look at a graph of it. That answer is not equal to 0. This thing is not going to converge. The series is divergent. What test did we use? Folks, we did not use the alternating series test. We didn't run 2 parts. Alternating series test always requires 2 parts. So what test is it that tells me if the limit is not 0, then it's divergent? Folks, we actually used the test for divergence. We thought we were going to use the alternating series test. It turns out we didn't need it. As it turns out, it's also true that if we let f of x equal the inverse tangent of x, then f prime of x is equal to 1 over x squared plus 1, which is positive. The thing isn't decreasing. It would have failed that way as well.